Okay guys, so let's move on to section 2.6, which is on constant acceleration. Here our goals are going to be to interpret velocity time graphs for information on acceleration and displacement, and to be able to solve constant acceleration problems using our kinematic equations. So we will see all of those things in this section. The first thing we need to realize is that changing accelerations can actually be pretty complex to analyze, but if you had a constant acceleration, this is actually a very common motion and it's much simpler to analyze and work with. We can use a simplified model for these problems of having a constant acceleration for lots of different types of problems, including cars that might be driving down the street. Free fall problems will have a constant acceleration, and lots of other objects could have that same type of model. So we're going to look at a model with constant acceleration. In a constant acceleration model, the instantaneous acceleration and the average acceleration are going to be the exact same thing, because again, your velocity is increasing or decreasing at the same rate throughout the motion. Your acceleration isn't changing, meaning that if it's constant, it's always going to be the same value everywhere. So let's zoom in on this graph a little bit and talk a little bit about the graphical representation of an acceleration and what that might look like in a graph. I want you to first look at this beginning leg of the trip here, or the piece of the graph here, where we have this nice straight line. It's something that'd be easy to find the slope of. Notice that in this section of the graph, as time progresses, your velocity is getting faster and faster and faster in the positive direction. Now, if your velocity is in a positive direction and it's getting faster and faster, that must mean that you have a positive acceleration in this portion of the graph as well. Notice what they've labeled down here, that when you have this object getting faster and faster in a negative direction, that's going to correspond to a negative acceleration. Now, anywhere you see these nice flat horizontal lines, in every one of these spots, you'll notice that they indicate that the velocity is constant. And if the velocity is constantly at any given value and it's not changing in any sort of a way, then that must correspond to a zero acceleration. So every one of those places would have no acceleration if the velocity was constant. Now, as we look at the rest of these pieces of the graph here, in this section of the graph, we notice that the velocity is getting slower and slower and slower. It started out as a positive velocity, but the thing is slowing down, which means that velocity and acceleration must be working against each other, and this must have a negative acceleration. On the other hand, when we look at this piece of the graph, we notice that this object is getting slower and slower because we see that its velocity is getting closer and closer to the zero line that we have up here. Now, if your velocity is slowing down and it is moving in a positive direction and slowing down, that is going to have a acceleration that would be a positive acceleration. So here you have a negative velocity because it's in the negative region of the velocity graph, but the thing is slowing down, so velocity and acceleration must be working against each other, and acceleration is positive. What I want you to notice as you are analyzing this graph here is that for every section of this trip, you can see that finding the acceleration would be easily done by looking at the slopes of these lines. Everywhere that we indicated a positive acceleration, we had a positive slope to the graph, here and here. Everywhere we indicated a negative acceleration, we had a negative slope to the graph, like here and here. And everywhere that we had a flat horizontal line, a zero slope on the graph, we indicated that we had a zero acceleration. So with a velocity time graph, it's actually very easy to find the acceleration. Look at the slope of your graph. Whichever the value of that slope is going to give you the value of your acceleration, and whichever sign you have on that slope is going to give you the sign of your acceleration as well. On this next slide here, we do indicate that. So if you want to jot some of these things down in your notes as we're working, that might be helpful for you. Again, notice that we've highlighted here the fact that the slope of a velocity time graph is equal to your acceleration. But what about displacement? Can you get any information about displacement from a velocity time graph? That answer is absolutely yes. You can find information on displacement from a velocity time graph by looking at the area underneath your graph. Notice that if you remember basic kinematics, the displacement that something moves through is equal to the velocity multiplied by the time. Now, if we had a constant velocity that was always at this one given value over here, and then we multiply that constant velocity by a certain time interval, we would find the displacement that the object moved through, velocity multiplied by time. If you look at the graph, you can clearly see that multiplying this value up here by this length of time is really just going to give you the area of this rectangle that you would find in that graph. So finding the area underneath a velocity time graph is finding the displacement of the object. When the graph looks a little bit different, like in this second graph here, and you instead have a diagonal line, you can still find the area underneath that curve very easily. What you could do is divide it off into a section that is a rectangle and find the area of that. So basically an initial velocity multiplied by some sort of time interval. And then look at the triangular portion of the graph and find the area of this portion. This portion would look at the height of the triangle as well as that same time interval. So the height of the triangle would be whatever your final velocity is minus your initial velocity for how high that is. Now here's the interesting thing. When we look at this concept that the area underneath the velocity time graph gives us the displacement of our object, we find that many of these kinematic equations that we see here are actually developed by simply understanding that. In fact, if you wanted to sort of follow along with some of these kinematic equations, you can look at page 53 in your books. All of these would work, and all of these can be used when your acceleration is going to be constant. If your acceleration is not constant, these particular kinematic equations are not going to work for you anymore. So be sure that anytime you're working with a problem and applying those kinematic equations, that you have a constant acceleration for that given portion of the problem that you're working with. Now, like I said, many of these equations actually come from the ideas that we simplified up here in looking at the area underneath these graphs. So if you wanted to kind of follow along with that, you can clearly see that if we take that initial velocity multiplied by the time, that's sort of finding the area of the rectangular portion, and adding on the increase with that would give you some of these equations like you have here. So that would give you sort of those pieces of the triangle being sort of that 1/2 base times height, and you're seeing that in these equations here. So each of these have a very logical foundation for where they come from. If you want to see more on these particular problems and utilizing these equations, you can look at the problem solving strategies on page 53 in your book as well. One last thing that I want to note while you're still looking at these kinematic equations is that your final position, your final velocity, and time can be things that change throughout a problem. You might look at various points in time when the object is in different positions, when it's moving at different speeds, and at different time intervals into the motion. Things that would not be able to change for a given problem, however, would be your initial starting position and your acceleration. Those things would be constant in any given problem. So let's look at an example to work together. We have an electron that's in a cathode ray tube of a TV set, and it's accelerated uniformly from 3 times 10 to the 4th meters per second to 5 times 10 to the 6th meters per second in a distance of 2 centimeters. And the question is, during what time interval does this actually take place? How long is this going to take the electron to be accelerated through that particular distance? Notice that my exponents here are really just big numbers. I don't know why that happened, but they're really big in here, so that's all right. So let's look at what kinematic equations would actually work in this particular problem. If you go back to your list of kinematic equations, you'll notice that one of the equations you had to work with was the xf equals xi, those are final and initial positions, plus 1/2 the final velocity plus, oh, sorry, that's the initial velocity, plus the final velocity. So just add those two up. So final and initial, add them together, divide them by 2, add on your initial position, and that should be your final position when you multiply those velocities by a time interval that this is running for. What we're going to do is we're going to solve this for t. So our final position is this thing ended up 2 centimeters away from where it started. I'm going to be sure that I put everything in SI units. So I'm going to put that as 0.02 meters for where this thing ended up. I can assume that it started at what I'm just going to call the origin for my problem, which is just at a 0 position. And now if I add on half of those initial and final velocities added up, I can place them into the problem as well and solve for time as the only variable that's left. Take a second and solve for your t, see what you get. You should find that the time is equal to 7.95 times 10 to the negative 9th seconds. So hopefully you got that too.